Hi everyone, welcome to the online causal inference seminar. Today we are excited to have Zijun Gao from USC Marshall presenting explainability and analysis of variance. As our discussion today, we have Artwen from Stanford University, and our Q&A moderator is Xinguang Zhao, who is also a collaborator of the speaker. We highly encourage the audience to put their questions in the Q&A panel, which is at the bottom of the Zoom window. With that, Zijun, the floor is yours.
Great. Right. All right. Cool. Can my screen be seen?
Yeah.
Oh, nice. Okay, great. So I will just directly start. Thank you so much for attending this online seminar. I'm Zijun from USC Marshall, and today I'm going to talk about causal ANOVA. This is a joint work with Qingyuan. So for the content, I plan to start by introducing the problem of explainability, and then talk about the problem setup, where I will try to highlight some limitations where people are trying to solve this problem using association-based procedures. After that, we will propose our solution, which incorporates some causal concepts, starting from the independent factors to the dependent factors, where I will try to highlight how the causal concept help with the limitations of the association-based analysis. After that, I will talk about how to estimate those quantities and illustrate on a real data set. So if you have any questions, feel free to put them in the chat window, and Qingyuan has very kindly agreed to handle that. All right, so without further ado, I will just jump into the intro. So I think in science and life, there is like a type of question that's pretty frequently being asked. So that is, how much a trait or an outcome can be explained by a factor or say a set of factors. So in genetics, scientists are asking similar questions. They want to measure, or they wonder, what is the portion of the trace variability that can be determined by the genes? And for that purpose, they propose a quantity they call heritability, which measures the ratio of the variance of the effect determined by the genes over the total variance of the trait. So to make this a bit more concrete, let's introduce some notations. Suppose we're hearing about something to be explained and determine that and denote that by the y. We believe it depends on the factors W1 and W2 through a deterministic function f. For now, we will just consider deterministic f, and later on, we're going to consider random f. And also, we start with a simple case where w's are independent. The function ANOVA, which is a pretty standard tool for analyzing the variance decomposition, works as follows. So I will have more details about this function ANOVA definition later on, but now let's just see what it offers. So it actually explains or decomposes the total variance of the trait y into that coming from the W1, that coming from W2, and that comes from their interaction. And by this variance decomposition, we're able to further attribute those variances to the explainability of each component. All right. So one thing we observe that is the function ANOVA is purely determined by the joint distribution of W1, W2, and Y, the observables, which we call association-based metric. So in the coming slides, I'm going to give two cute and small counterexamples showing this is not that perfect. All right, so our first counterexample is what I call the 0-1 game. So suppose there is a game machine where the players will pick either 0 or 1 and receive a reward or not. And then, sorry, I lost my slides. Okay, and then Alice decided to give this game a try. But she doesn't really know what happens behind the stage. So she decided just to flip a fair coin and decide between the numbers. After playing this game for a few rounds, Alice saw that no matter what he chooses, he will always get the reward about half of the time. Then based on that observation, she thinks to herself that, my choice of 0, 1 has nothing to do with the reward, or zero explainability in our language. However, what happens in this game machine is there is actually a Bob hiding behind the stage. So in this machine, the Bob actually guesses what is Alice's choice, either 0 or 1. So if Bob got it right, then he wins. Otherwise, Alice wins and she got the reward. And Bob doesn't really know Alice in person, so he also decided to just toss another independent fair coin and make the bet. So that's why the Alice's reward appears like 50-50 despite her choice. However, from Bob's perspective, the player, that is Alice, definitely have a say in whether she got the reward or not. In the sense that suppose Bob has already submitted his guess and Alice changed her mind at the very last minute, then the outcome would have changed. So now we have two conflicting perspectives of Alice's explainability to whether she received the reward. From Alice's side, she only observed the joint distribution of the pig and the reward, and she thinks she has no explainability. Well, on the other side, Bob thinks, well, you of course have effect on the final reward. This is because he knows what will happen in the counterfactual world. So this example shows that if we only focus on the joint distribution of the observables, then that may lead to some misleading conclusions about explainability. All right, now let's move on to the second example, which I call weather report. I believe that all of us know sort of like how the weather report on TV works. So there will be some model or a group of scientists, they will try to come up with a forecast, which is later passed to the broadcaster. And the broadcaster will be basically read that off on the TV so that people can listen to whatever he says. So in this scenario, we, by common sense, know that the weather model is the real driver behind this forecast. So it should have 100% explainability. But the broadcaster simply just relays whatever the model says. So he or she should have no explainability to this forecast at all. However, if we look at the association-based analysis, then it's pretty tempting to assign equal probability, or sorry, explainability to both the broadcaster and the weather model because they appear the same all the time, like equally explanatory. And this example shows that when we consider the explainabilities, we not only have to look at what are the joint distribution of the observed variables, we also need to consider what are the dependence between them, or what we call the causal ordering. All right, so now we have seen two examples illustrating that association-based analysis may not be sufficient, and that motivates us to propose something incorporating the causal concept. In particular, we're going to leverage the counterfactuals and the causal ordering so that it can avoid the dilemmas or the conflicting things we saw in the examples. Particularly, back to the 0-1 game, in the game machinery I just described, the function ANOVA will assign no explainability to Alice, while our causal ANOVA will assign a positive explainability, which is more consistent with how we understand the mechanism. And in the weather report example, the functional ANOVA cannot distinguish the model and the broadcaster. So it gives a 50-50 split. However, our causal ANOVA capture the dependence of the broadcaster on the model. So it assign all the explainability to the model and nothing left for the broadcaster, which is what we believe a fair attribution. All right, so this is just an overview of what causal ANOVA can achieve. And in the next slides, I'm going to unwrap the details of the causal ANOVA. Okay, so first I will formulate the problem a little more rigorously, incorporating two key concepts from the causal world. So the first concept I leverage is the potential outcome model, which I believe is very familiar to the audience here. So we consider there are multiple treatments. We also call it variables or factors. Sorry to use them exchangeably here, which is denoted by W1 or 2 WK. We denote the potential outcomes, Y, as something that could be affected by the values of all of them. Here, the function f could be either deterministic or random. For the observables, we're going to only see one out of many potential outcomes, the one corresponding to the realized treatment level. All right, so that's the first piece we use in the causal world, potential outcome model. So next, I'm going to leverage the causal orderings to model those treatments. So assume that the treatments actually follow a directed acyclic graph, short for DAG. In particular, if we change some treatment's value and that has nothing to do with other treatments, then we call them causally independent. Here, the causal independence is a stronger notion of independence in the sense that it actually implies the probabilistic independence, while the reverse is not true. To think about a difference, let's consider the 0-1 game, where Alice's pick has something to do with the reward. So those two are not causally independent. But if we think about probabilistic independence, the Alice picked number is probabilistic independent of whether she received the reward or not. All right. Beyond the independent treatments, a more interesting and also more challenging scenario is we have the dependent treatments. So here, the W1, W2, WK are modeled using the DAG, and changing the treatment values may affect other treatment values. With a loss of generality, I will just assume that WKs are ordered decreasingly in the topological ordering, and the potential outcomes below reflect that dependence. All right, so that's sort of like the model we work with, and now let's specify our goal. So what we want to achieve is, by using the potential outcome model and the treatments modeled by the DAG, we want to quantify the explainabilities from the causal perspective. In particular, for a subset S contained in all possible treatments cardinality A, we aim to define the total explainability of all the variables in S, and also the explainability of the interactions for variables in S. All right, so that's our goal. Now we know that where is our destination, and next is let's try to achieve it. So let's start from the simpler case where the treatments are essentially independent. All right, so to talk about the definition of causal ANOVA for independent treatments, I would love to bring back the motivating example heritability and take the fraternal twin studies from that. The definition of total explainability in causal ANOVA is partially motivated by that. So in a previous work by Qing Yuan, they were considering the contrast between the outcome of a fraternal twin, where they have non-identical genes, but the same household environment. Here, we can consider the G and G prime as an independent copy of each other, given their parents. And we look at the contrast. Oh, sorry, this means the contrast of the two outcomes as the variability caused by their gene isolated from the variability caused by the environment, because the environment is fixed. Then we use the variance of this contrast to measure the influence or the explainability of the gene. And we do some proper normalization to ensure the ratio stays between 0 and 1. So that is the causal ANOVA concept for the total variability of a single vector gene. And this can be easily generalized to an arbitrary subset S. There, things are pretty similar. We just take the contrast of the outcome with only the components in the S altered, the rest fixed. We use that variance and do some normalization to ensure the values stay again in 0 and 1. So this quantity or total explainability will always be identifiable for causally independent factors and also satisfy some desirable monotonicity, which simply says that if we increase the set of variables, then the total explainability is going to increase, or say at least stay the same. Another thing we find pretty useful or convenient is that we can illustrate the explainability numbers using the Venn diagram. As shown on the right-hand side, we have a Venn diagram consisting of two factors. So the red circle basically represents how much variability the W1 can explain. The yellow circle corresponds to how much variability W2 can explain. And this H shape or infinity shape corresponds to the total explainability of W1 union with W2. So from this Venn diagram, it is pretty easy to read off that the union has a larger area, so larger than each individual circle, which actually corresponds to the monotonicity we highlight on the site. All right, so now we're done with defining the causal ANOVA total explainability. Now let's shift gear and talk about interaction. So to define that, I will again go back to the fraternal twin study, but this time we're considering 4 brothers, or say 4 words, where the worlds will differ regarding the genes GG prime and the environments EE prime, or both. So suppose there's really no gene environment interaction, then the combined effect of altering both should be the summation of the effect altering each of them and sum up. Any deviation from that will be considered as interaction. So this type of deviation can be captured by the difference in double difference on the left-hand side. Therefore, we are going to use the variance of this double difference with some proper normalization as our metric for the explainability of the interaction between G, the gene, and E, the environment. As the extreme case, suppose this quantity is exactly 0. Then that means there's absolutely no interaction, and the effect of G and E are purely additive. That is the interaction of 2 factors, where the definition can easily extend to arbitrary subset of S containing K using the anchor decomposition. So anchor decomposition is defined as follows, where we take a function f and break that into the summation of several pieces denoted by is. So is can be considered or interpreted as the interactions between the variables in S, where this alternating signs ensure that the lower order interactions in S are canceled. So this is a bit abstract, Let's consider some concrete examples. So suppose we only have two factors, G and environment, and we let the subset S to be just one. Then this IS is basically the change in outcome, thus we change the W1. And for the second case, which is more like interaction, we consider subset S to be 1, 2, then this IS is basically the double difference we saw on the last slide. All right, so based on this anchor decomposition, we're going to use the variance of the IS, the interaction of variables in S, as the numerator, and normalize that by the variance with some constant to ensure it stays between 0 and 1. And that is our definition of the explainability of the interactions for S. So this definition also satisfies another type of monotonicity, which basically means that the higher order interactions are going to be more specific, but explains less. All right, so far we have finished talking about how to define the total and interaction explainabilities in the causal ANOVA world. But we did that in separate lines. In fact, we can unify them in the following way. So there is straightforward connection between the total and interaction using this formula, which says the interaction explainability is basically the individual sum up minus the total of their union. This is the two-factor case, and a more general expression like this can be get or described by the inclusion-exclusion principle outlined here, which basically says the interaction is the summation of the totals with this alternating sign. So this connection actually allows us to map both the total explainability defined and the interaction explainability defined into the same Venn diagram. We already see that the circles are the explainabilities coming from each individual W. The H shape or infinity shape is their union. And now we say the leaf in the middle corresponds to the interaction. And the area calculation based on this Venn diagram basically give us this equation. So this slide seems to suggest that our definitions of the total and the interaction can be explained in some way, unified in some way, as a measure on this canvas, or say corresponding to this Venn diagram. This is actually true, and it can go a bit further. So in the coming slides, I'm going to show you that a measure on that canvas or on the Venn diagram can unify our total interaction explainabilities and also some other concepts from the global sensitivity analysis, where Art is definitely an expert in that domain. All right, so to talk about the global sensitivity analysis, I need to introduce a bit more notations. In particular, I promise you to talk about function ANOVA. So function ANOVA decomposes a function f into the summation of a few pieces denoted by fs, where this is different from the anchor decomposition, which I used is. The good property of this decomposition is that if the treatments are independent, then those pieces are orthogonal. And this orthogonality allows us to decompose the variance of E and F to the summation of the variance for each pieces Fs, which we saw pretty early on in the presentation. So this sigma s squared serves as the basic of defining several sensitivity indices, which we see on the next slide. So here we just talk about three of them, which are arguably the mostly used quantities in this area. Well, the first one is what we call Sobol's lower sensitivity indices, which basically sums over all the variance for the set that is contained in our target set S. So what it does is it measures all the variance explained by the variables in S and their lower interactions, but it doesn't include any variance explained by the interaction between S and things outside S. First, next, let's talk about Sobol's upper sensitivity indices, which is defined as all the variances where the S prime has some overlap with the target set S. So this is measure all the variances where it's partly explained by the S, or say the S has at least some influence there. Finally, we also want to talk about superset importance, which consider all the variances or for the S prime that contains S. So that essentially says all the interaction, higher order interactions where the members at least contain all the members in the subset S. To draw a connection between the causal ANOVA and the existing global sensitivity indices, when the F function is deterministic and the treatments are independent, then our total is basically the Sobol's upper index, and our interaction is the superset importance. All right, so that's the notation introduction section. And now let's see how they can be unified. So basically, this theorem tries to say that the four concepts, the Sobol's upper, lower, superset importance, and the function ANOVA, can be unified in the measure defined on the explanation algebra generated by the K treatments with the logical operations conjunction, disjunction, and negation. Particularly, we can define we have four ways of defining measures by specifying the area for a subset of the algebra and then extending to all the sets in the algebra by additivity. Particular, the first definition here uses the Sobol's upper index, which specifies the area for the three pieces on the right-hand side. The second is using the superset importance or the interaction explainability, which specifies the area on the right-hand side for those three pieces. The third one uses a Sobol's lower index and let us know what are the variability. It can be slowly explained by some variables or some set. And finally, the fourth one uses the function ANOVA and define the area for those disjoint regions. So this theorem says that no matter where we start with, we'll either start from the total, the upper or the superset importance, etc. We're going to end up or arrive at the same measure on this explanation algebra. So in some sense, they are unified, or they are just different perspectives of the same thing. Moreover, this measure is actually desirable in the sense that among all the measures on this explanation algebra, this is the unique measure that satisfies a bunch of axioms, which we find sort of natural or desirable. And for more details about this part, I would recommend referring to our paper. All right. So the last piece I want to squeeze in the causal ANOVA independent factor is the comparison with Shapley value and the Shapley interaction index, which is where the Shapley value is pretty frequently used in the game theory world and now the machine learning world, where they try to attribute the reward to different players or different features. So the Shapley value starts by assigning a value function for each treatment, each subset of treatments. And here we can just use the total explainability. And then it can be defined in this way, which I will not go to the details. So a property enforced by the Shapley value is the individual contributions will always sum to 1. Where in contrast, our causal ANOVA total explainability can sum over 1 because we may have some overlap in the middle, or say interaction. Moreover, there are several ways to extend the Shapley value to describe the interactions. And here I just talked about one of them, which is sort of a popular one called Shapley interaction index, where the definition is written here. But we find one thing about this is not so desirable for explainability is that this value can go negative, which is contradicts with how we understand explainability from the common sense side. All right, I'm going to mention Shapley value one more time as we talk about dependent factors, so stay tuned for that. All right, so now I've finished talking about the causal ANOVA for independent treatments, where we define both the total and interaction explainabilities and draw a connection with global sensitivity analysis. So there have been a lot of efforts in extending the global sensitivity, say function ANOVA, from independent factors to dependent factors, which could be quite challenging because when we have dependence across factors, then the orthogonality in function ANOVA typically breaks. And that can bring in, say, negative variance component or other computational issues. So next, what we're going to do is extending our causal ANOVA to dependent treatments, which preserve the non-negativity, and more importantly, incorporate our DAG knowledge among the treatments. So let's see how we do that. So to motivate our definition for alpha causal ANOVA for dependent treatments, let's go back to the second counterexample, the weather forecast. So there, we sort of think intuitively the broadcaster should have no explainability because it simply follows or copies the weather model and adds no new information. So this intuition or interpretation motivates us to define the explainability of dependent factors by looking at its intrinsic randomness. Or more rigorously, we're going to extract the intrinsic randomness and use their explainability as the explainability of the dependent factors. Right. So in this presentation, I will focus on talking about the concepts under this non-parametric structural equation model with independent errors, short for NPSEMIE. But we have more general definitions in the paper using basic potential outcome schedule. So in NPSEMIE, the treatments are obey a set of structural equations that is consistent with the DAG. Particular, each treatment can be written as a function of its parents and some intrinsic noise, EK, where the EKs are causally independent. Great. Then we already know how to define the explainability for causally independent factors, which is talked about like maybe 2 or 3 minutes ago. So we define it, and we let the explainabilities of the W's to be just those of the intrinsic noise. So as you imagine that the good properties of the independent factors from the independent factors will be automatically inherited to the dependent factors. Particularly, the matrix will always be non-negative. However, we find this definition also have a desirable property, which we term ancestral consistency, which is good for trading the cost. And let me illustrate a bit more. So the ancestral consistency is useful when we consider a set of graphs, for say a graph expansion. So suppose we have a graph G on the left-hand side, and now we want to expand it to the graph G prime on the right. And consider S in the red frame to be an ancestral set, meaning that it contains all its ancestors, while here is itself. And on the expanded graph, we can find the S prime, which is the smallest ancestral set containing the S. And this ancestral consistency basically says that the explainability of S in the original graph G is the same as that of S prime in the expanded graph G prime. And back to our weather forecast example, what we can do is we can expand the original node weather model by finding the components or inner components or the steps before that. Particularly when we have some data, when we have some meteorologist. And this ancestral consistency basically says that the total explainability of data plus meteorologist plus the weather model is the same as that of the weather model before the graph expansion. So basically, we can start from a simpler graph and gradually trace causes without worrying about inconsistency. On the other hand, we can also work reversely and collapse a graph. In this example, we can say, let's remove the broadcaster, and we have a graph with two nodes, weather model and rain forecast. So this ancestral consistency basically says that the explainability of the weather model will remain invariant before and after this graph collapse. So one thing I want to highlight here is this ancestral consistency, which is satisfied by the causal ANOVA, is typically not satisfied by Shapley value. As you can imagine, in Shapley value, the total explainability or value of individual players are forced to sum to 1. And if we add more players or features or variables into the play, then the value or reward are redistributed. And each node or each player is likely to receive a smaller reward. All right. So coming back to the causal ANOVA definition for dependent variables. So far, we have seen the good sides of this definition. But there is definitely something urging about this definition, and that is identification. Sadly, different from the independent factor case, the causal ANOVA concept for dependent factors is generally not identifiable. And the intuition is that the causal ANOVA quantities depend on the joint distribution of the potential outcomes. But what we all observe in this world is the marginals. To construct the joint from the marginals, we need extra structural assumptions. Particularly, a set of a handy and also like used up sort of like prevalent assumption about the joint distribution is comonotonicity. And under this comonotonicity, we basically can determine the joint from the marginals, which enable the identification. And examples of this comonotonicity includes but not limited to the causally independent treatments we talked about in the first half, and also the NPSEM-IE with additive points. So in the following, for estimations, we will focus on the comonotone case and leave the broader and more challenging partially identification set identifiability problem for future research. All right. So, so far we have finished defining the causal ANOVA for dependent treatments, where we basically do two things. First, we extract intrinsic error, which are causally independent. And then second, we apply the causal ANOVA concept from independent treatments. Done. And next, I'm going to talk about, so that is more about the definition side. And next, I'm going to talk about how to estimate those quantities and also demonstrate on a real application with dependent factors. All right, so recall that by the by the exclusion principle. If we know what are the totals, we basically know everything we want. So we'll focus on estimating the total explainabilities. And let's start from the simple case where we have an outcome oracle that if we input some treatment values, it will give us the corresponding outcome. We also assume that treatments are causally independent, and we know how to generate the independent copies. And in this beautiful world, we're able to estimate the explainability pretty easily using a scheme called peak and freeze. So basically what we do is we generate a pair of W and W prime S, the independent copy, ask the oracle what are the corresponding Y's with only the S parameter changed, and we check their difference. We repeat multiple times and use the empirical variance as the numerator for our causal ANOVA quantity. The denominator is just a variance, pretty straightforward to estimate. All right. So in this case, independent factors with an oracle is pretty easy to deal with. Then let's move to the more real world case where we have dependent factors and we have no access to any sort of oracle. So here, to enable the identifiability, we assume the potential outcomes are comonotonic. So the concept here is we try to learn a generator from the intrinsic noise EK to the outcome. And we apply the previous pick and phrase scheme. And to achieve that, well, we basically learn the computational distributions of each variables given its parents, as well as y given w, and then revert that. So like we got a bunch of computational quantiles. And then to apply the pick and freeze, we generate the intrinsic noise ID from user one, and recursively along the DAG, compute the corresponding W and Y, and the rest is the same as the pick and freeze. All right, so that is the estimation of scheme for dependent factors with no outcome oracle, which is what we're going to apply to our real data analysis. So here, I demonstrate a causal ANOVA on two income datasets, the UCI from 1994 and ACS from 2018. The outcome or the variable to be explained is the log annual income, and we consider three factors: sex, race, and education. In particular, we focus on the US-born adults, and we split the sample into 8 age groups. Each spent about 5 years. Recall that for dependent factors, a key thing our analysis require is the DAG, which we specify on the right. So we think the race and sex are more like root nodes. They both can affect education, and all three may have a say in the income. So this is the estimation. This is the case where we have no oracle dependent factors. So we assume a comonotonicity and learn the conditional distribution using the attributes. So let's see the results.
Hi, Zijun. Sorry to interrupt. It would be nice if you can wrap up within a couple of minutes to leave enough time for the discussion. Thanks.
Yeah, sure. I think I only need 2 or 3 minutes. That will be okay. Okay, I will continue. So the explainability, so I start from the group that is most relevant to me, that is the data collected in 2018 for age 25 to 30. I visualize the explainabilities using the Venn diagram with the number superimposed. So there we see education has the highest explainability, followed by sex and race. And there's a small like sex and education interaction. Then I am sort of curious to see how does this Venn diagram varies across age groups. So I just do the same thing, but for 40 to 50, 45, and 55 to 60. We can see that the education explainability increased or almost tripled and then decrease a bit. And the explainability of sex increases and then stabilizes. The interaction also increases a bit. So this seems to suggest that the sex becomes a more important factor as the family work balance kick in. Moreover, I'm curious about what is the case in my mom's age. So I go back to the data 1994 and apply the same analysis. So if we compare across 1994 and 2018, we see that education in general explains more and sex in general explains less. And the interaction also decays, which is sort of like consistent with our perspective that we're now more and more evaluating the candidate's ability, like reflected by education, rather than like sex and race, which is good for me. All right. So finally, we also illustrate that our procedures are invariant regarding this ancestral consistency, where we try out different graphs and compute the values and see they're roughly the same. Okay, to wrap up. So in this talk, I introduced the causal ANOVA, which is an extension of function ANOVA that quantify the explainability of a total explainability of a set of factors and also their interactions. This can be applied to random outcomes as well as dependent factors. And also is sweet to visualize and iterate. For future directions, Qingren has already launched good works regarding incorporated covariance and consider conditional explainability. Another direction of interest will be leveraging the generative models for the estimation of those quantities. Because essentially what we do for dependent factors is train a generator from the intrinsic noise to the final outcome, where we hope to leverage the rapidly developing generating tools. And finally, partial identification is always on the radar. All right. So with that, I conclude my talk today. Hopefully I'm not too much over the time. Thank you so much for being in the audience, and I'm very much looking forward to the discussion by Art.
Thanks, Jijun, for the fantastic talk. For the interest of time, maybe we should switch to the discussion first. I see there's one more question in the Q&A, but maybe Xinguang is already typing. Thanks. Art, the floor is yours.
Okay, well, thank you. I'm so happy to see causal inference connecting up with global sensitivity analysis, two of my favorite areas. I'm going to click to share my screen, and here we go. If you go into presentation, and what you should see is are my slides. So here's a comment. I'm going to start off a little philosophically. What does it mean to explain some kind of a variable? It's kind of hard, but usually if you can explain the importance of other variables to it, that's a good way to start. And sometimes, like especially if you're making decisions, you may want those explanations to be causal. Okay, so I read this paper, I quite liked it. They have a way to quantify causal importance using global sensitivity, Sobol indices. There's some nice general visualizations. I liked those Venn diagrams. And then they have some axioms, characterizations, a few paradoxes that get you thinking. And I've been reading in this area for many years, but I saw lots of new references to me in that paper. I'll begin with what does it mean for a variable to be important? And the variable A, it's important if changing A changes B, and B is important. And so you can transfer importance, but you cannot create importance. So suppose you have a function of D variables, and you want to know how important is xj. What are you going to do? Well, you change xj and then see what happens. Okay. Then you have a decision. Well, where should I change it from? Maybe I start just at the default, or maybe I select from a distribution. We've got to start it somewhere. And you got to change it to something. I could make like a local perturbation or a global, or maybe I sample from some distribution, but I have to answer that question too. While I'm changing xj, what happens to xk? I could leave it fixed, But if I'm adding bedrooms to a home, maybe I want to also change their floor area ratio. It's not obvious what to do with the other variables while you're changing the first one. Now, suppose you have thousands of these numerical changes that you've measured. Well, how do you boil them all down to one number for xj, xk, and xl to just compare them? And there's lots of different choices for how you summarize those into one number. And then when you're done, oh, what's the importance of a pair of variables or a triple of variables and so on? And there are thousands of these. I found dozens of survey articles. There's just lots and lots of ways to measure importance. The easiest case is when your function is additive and the things going into it are independent. Now all you have to do is say, well, how some kind of a semi-norm on these functions, and it separates out nicely. But sometimes it's not additive. What happens when you change x1 could actually depend on x2. You could have interactions. And if you have interactions of independent variables, I would say Sobol indices are an extremely sweet solution, and we saw those in use today. What if they're dependent? Okay, then you may shift to Shapley value. That's a long story. They cover it in their paper, but I think today we don't talk about Shapley. Okay, so here's the context in a causal inference setting. You have a directed acyclic graph. You want to know what's affecting this output node y, and you can question whether there's statistical independence or causal dependence. How do you sort out the relative importances of A, B, and C? And the causal ANOVA, or random causal DAG, starts off by bringing in latent variables. So every one of these vertices has a latent variable attached to it, and those are statistically independent. And so what's going to happen at B, it's a deterministic function of whatever comes in on this arrow plus one piece of noise. And what happens down here for Y, a deterministic function of all the incoming arrows, including one that is noise or randomness. Now, if all of these things are independent, we can quantify everything using Sobol indices. So Sobol indices grow out of the analysis of variance. Okay, so it's a little more than a century old, Fisher and McKenzie. And when you teach ANOVA, you might have a thing like this, a table of numbers equals a constant table plus a table that's constant in columns plus a table that's constant in rows and an interaction. And what's going on is the row you're in is independent of the column that you're in if you grab an element of that matrix. And it turns out all you really need is, well, independence and finite variance, and then you can run an ANOVA. And so you start off with a function that's a constant function, and then you add in a function that's just one of the variables, and an interaction is a function of just two of the variables. And if we want the variance component for a set, or if we want the effect interaction for a set of variables, well, we don't want to attribute any of the proper subsets, so we subtract those all away, and then we condition on what's left. And conditioning on those guys just means integrating out the others. Okay, so that gets us variance components, so the variance of all those ANOVAs and main effects, and they sum to the total variance. Okay, so now we can partition things. And Sobol indices that we saw today, well, the Sobol index for a variable is just its mean square, and min effect to mean square, the lower index. The upper index, you toss in every single interaction that contains that variable. Two different notions of importance. And then they generalize to sets of variables. And we usually normalize them so that as a proportion of the variance, like an R squared. Now, you don't have to actually estimate the interaction, square it, integrate it, and sum it. You can use pick freeze identities, and there's lots of these. Let me show you this one here. So you can take f of x, and then you can go in and pick fresh values for some of the variables, call it z, and leave the old ones where they were. And now square that. Well, if those were really important variables, this mean square is going to be big. And if they weren't that important, it's going to be small. And when you divide by 2 and take the expected value, what you end up is Sobol's upper index. And there's another one of these tricks to get Sobol's lower index. And there are maybe dozens of tricks like this. I call them generalized Sobol indices. Lots of different things that you would want. You can use pick and freeze to estimate. And one of my favorites is if you just add up all the Sobol indices for variables one at a time, you get a cardinality weighted sum of variance components. Okay, so now back to this nice paper by Zijun and Qingwang. One of the things they showed us was like reverse to George Box. They can show us all these examples. All those models are correct statistically, but some of them are not useful. So this is like the opposite of what George Box would have said, that all models are wrong and some are useful. It's doubly opposite. Okay, so then you have to think scientifically, well, which of those models is the one that's going to answer the question you want? One of the things that comes up, and they alluded to this, is the causes of effects. So when you're doing this kind of attribution, you're trying to find the cause of some effect, whereas potential outcomes are looking at the effects of some cause. And now you have this problem that, well, what about the cause of your cause of the effect? Or the cause of that cause? Or onto some level of, um, you can carry that on to some other number of levels. Okay, so that's what makes attribution, one of the things that makes attribution pretty hard is you have to look at the causes of your causes. In fact, if you write everything as a set of random variables and they're on a sample space, well, a random variable is a function of omega. So basically, omega causes everything. Now, this isn't going to be scientifically useful. It's a kind of causal collapse and correct but not useful. You need some scientific interpretability, and you'll see those in the examples of their paper. So they're not giving you the causal collapse. Okay, so what's going on? The old explainable AI just went from data to variable importance. Now they go from that, you can go from a DAG to variable importance, which has some more scientific credibility. And now you've got a debate. Okay, which DAG? You don't go out and observe a DAG. You have to kind of speculate, or you have to use scientific understanding to choose one, and what distribution to choose. Okay, so I think these are incredibly hard problems, but I think that's also the proper place to have your debate. In about a minute, I want to mention another issue that they don't talk on, but it's below the surface. Far, far harder. What about a one-off explanation? So there's this nice paper by Dawood and Muzio on cause of effects and effects of causes. The example they have is, well, did Lipitor cause Juanita's diabetes? And my take on that paper, maybe they don't summarize it the same way, is you're not going to get there using Bayes, and you're not going to get there using potential outcomes. And yet, the court has to get there. And this is an example, let's see, in explainable AI, you might want to know why was your uncle's loan declined. You actually have the black box function that did it. You can change all the variables, and it's still hard. And these authors and many others point out that a problem that there's no ground truth in variable importance. You can't have Kaggle for variable importance. Okay, so I want to thank for some funding, and I want to thank the authors of that paper and the OCS organizers, especially Aditya, who's been helping me get ready for this.
Thanks, Art. I'll ask Zijun to quickly get back to the discussion.
Oh, thank you so much for the kind discussion. And it's actually my first time to see like the philosophical side of art. Actually, I already used up my time, so maybe I want to give the final a few minutes to Qingwen and see whether he has something to comment based on either my presentation or Art's discussion.
Okay, thank you. Not really anything. This is a great presentation, and thank you, Art, for the comments and actually Art has been giving us comments throughout this work. So we have found them to be incredibly useful. So I guess Zijun's presentation kind of reflected our thought process, which we started from thinking about counterfactual contrasts and trying to define some variable importance in terms of counterfactual contrast, which you can use to define total explainability or interaction explainability. And at some point, we noticed some connections to function ANOVA, and we asked Art, and Art told us that this formula you have, this is the pick freeze method for computing Sobol's indices. So it's very nice to kind of see that connections. So I guess I would still say from my perspective, maybe from a counterfactual inference perspective, I found it more natural that I mean it's easier for me to think about the pick freeze as the definition of total explainability or Sobol's upper index instead of the function ANOVA, but I guess it's just a matter of perspective. Yeah, thank you, Aditya, for hosting us. And there's one question in the Q&A. Is there any situation with causal ANOVA with computational problems that is estimates hard and costly to compute? And certainly there is. So as kind of Zijun kind of alluded to, you have to kind of fit these distributional models according to your DAG. And then to compute these quantities, you have to generate new noise variables. So there's a lot of computational problems, so certainly. Yeah.
Right. Thanks, Jiyun, for the fantastic talk, and Art for the fantastic discussion. And also thanks to Qinguang for sharing your thoughts and also handling the Q&A. Let me close by quickly sharing, announcing the next week's OCIS. So next week, there's going to be another joint webinar by the Society of Causal Inference and us, the OCIS. It's going to be a panel discussion on funding your work, thinking beyond the NIH. The panelists are going to be Michael Thompson from University of Michigan and Shu Yang from the North Carolina State University. Thank you all. Let me stop here.
Thank you.